Hello everyone. Today we will be looking at some of the basic concepts and ideas in electromagnetism. We will take a quick look at charge carriers and their features such as how they interact with one another and how they produce an electric and magnetic field. We will also look at charge carriers and a current as well as some applications such as a solenoid.
A lot of electricity is explained using the idea of electric charge. Particles that have charge can be called charge carriers, which comes up a bit more when talking about circuits. The size and mass can vary, but only the charge is meaningful here. Charges produce electric fields, which in turn exert forces on other charges. While you're probably used to the saying opposites attract in the context of magnets, it works equally well for electric charge. Positively charged objects like a proton will be drawn towards negatively charged objects and away from other positive charges, and similarly for negatively charged objects like electrons. How much force that is depends on the amount of charge each object has, and so it becomes easier to talk about how much force or expended energy it would take per unit of charge. How much force at any given place is the electric field, and how much energy it would take to move something there is the electric potential. Potential especially helps to make problems without charges much easier. Finally, when charges move, it's called a current, and the moving charges then produce a magnetic field.
In a wire, charges will move from a high potential to a low potential. This movement is called a current. The speed at which this current flows is determined by the potential difference. You can think of this as a waterfall. If the waterfall is high, meaning that the potential difference is large, more current flows. As the current flows, it produces two fields, the electric and magnetic fields. The electric field is easy to visualize. It just looks like a hill. This indicates that the strength of the field is weaker the further you go from the wire. The magnetic field is similar, but the direction is determined by the right-hand rule. If you visualize that the current is going up, the magnetic field is spiraling around the wire in a counterclockwise direction.
A pretty good example of this interrelatedness is the solenoid, which is just a fancy name for a coil of wire. The fields from each loop add to each other, which results in a very consistent field on the inside of the coil. The right-hand rule applies to the direction of this field as well as the component parts. Curl your fingers in the direction of the current, and the field points in the same direction as your thumb. Ordinarily, the generated field would have a full rotation around the wire, but the other loops cancel these out. The field ends up pointing almost entirely through the solenoid and only really changes at the endpoints. The field is also mostly constant outside the coil as well. As you might expect, the ability to produce a constant field is valued, but it's not actually the biggest use of these. Moving a magnet through or near a wire creates a current in that wire, and that happens to be repeated if you have several loops of wire next to one another. And this way of creating electric currents is actually the most used way of doing so. Forms the basis for nearly all power plants. Even the more exotic ones are still turning turbines, they just have other ways of heating the water.
In summary, we have seen how charges interact with one another and how a magnetic field is produced. We have also touched lightly on some applications like power generation. Join us next time as we cover some other basic concepts in physics.